So we want to look at the interpretation of partial derivative. What does it mean geometrically? Well, let's look at it first. So geometrically speaking, let's think about a function z equal to f of x comma y. So the function represents a surface, okay? A surface S of the graph is the graph of f, right? And normally speaking is something like this, right? You have this. So z usually represent f of x, y. It's a surface in the space. All right, at any given point, let's say A, right? A, B, and this is z equal to f of a, b. So what does that mean on the derivative at that point? Well, let's look at this. If we fix y equal to b, meaning we only allow y equal to b on this line right here, the surface, okay? Y equal to b, we are restricting our attention to the curve C1. Let's look at here, C1. We are only look at this curve right here, C1. This curve, C1, on the surface. And this is the curve intersection between y equals to b is a plane, because that's a constant. We look at that only at this intersection between the curve and the plane, y equals to b, which is the curve right here, C1. Okay? And we'll look at the point at AB. So on this plane, there's a tangent line right here called T1. And we'll look at the slope of tangent line at that point, rate of change. Similarly, if we look at the derivative with respect to y, when x equal to a, now we're looking at this curve C2. Right here, C2. Right, we're looking at this plane. Sorry, my bad. Not that. We look at this plane, x equal to a intersecting with the curve, with the surface. So you have that. Therefore, you have what? On the surface, you have a intersections, which is what? It's slope of tangent line of the curve C at the point A, B, C. And then the second derivative, the first derivative with respect to y at the point is simply the slope of tangent line on that surface, on that plane, x equal to a. So that's pretty much says that interpretation of that. So the partial derivative of f with respect to x and y respectively can be interpreted geometrically as a slope of the tangent line to the trace of C1 and C2. We have C1 right here and C2 right there, okay? And this, in the planes y equals to b, that's in the plane y equals to b right here, and in the plane x equal to a, which is this one, T2. So as we have seen in the previous case, the heat index functions, kind of represented that, right? It's one or the other. So sometimes we use the notation del z, del x, or del z, del y, representing the variations, and the meaning assume other constant. So here we assume y a constant. Here we assume, since we see the variation of y, then we assume x as constant. So I cannot emphasize this enough. All right, let's look at an example here. If xy equals to 4 minus x squared minus 2y squared, find the partial derivative of f at 1, 1 with respect to x and with respect to y. And what does it look like? So first of all, take a derivative, right? That's not bad. So partial derivative with respect to x, you get negative 2x because the other two are constants. And then you plug in, add 1, 1, you simply replace x by 1. You get negative 2. Partial derivative y, now you look at here. So 4 and x squared are constant, so you have minus 4y right here. And replace y by 1, you get minus 4. All right, so what does that mean? If we look at this graph, so partial derivative with respect to x, meaning we're treating at y equals to 1 as a constant. So here, y equals to 1 a constant. You see the curve right there. right? Intersection with that, right? So that would represent -2 is the what? Is the slope tangent line. Similarly, so that's the curve of y equal to z equal to f of x, y, right? That's the curve. Similarly, if you look at the partial derivative with respect to y, then now you're fixing x to be a constant. So on this plane, there's intersection between the plane and the curve representing the surface. Right, here's curve 2. And this is the what? Slope of tangent line here is -4. So a function of more than 2 variables will do the same thing, right? We can have as many variables as you want. So once we take a partial derivative with one variable, the other will be treated as a constant. The other variables will be treated as constants, okay? So you can have as many as you want. So once we do this partial derivative with the ith variable, then the other one will be treated as a constant. X1 doesn't change. The only thing vary is x sub I right there, okay? We also write the notation as with respect to x sub I, the ith component. Let's look at derivative here. Example here. Find the derivative of f sub x, f sub y, and f sub z if the function like this. So we'll take a derivative with respect to x. We're going to only treat x as a variable. So derivative of e to the xy is e to the xy, and then with derivative of this component with respect to x, which is 1, so you have y left right here. This is coefficients. Similarly, we take derivative with respect to y, same thing. Now we take derivative of e to the xy, treating only y's variable, so derivative of e to the xy is still e to the xy. Then derivative of x times y, y is a variable, y become 1, so x is still there, natural log z. Finally, take derivative with respect to z. We're going to treat these two guys, the first guy, as a constant. So derivative of z is 1 over z. There you go. So that's a partial derivative with variables more than 2.